This is active filter design, lecture 11. So far we have seen several things. First is how one can approximate a desired magnitude response by a ratio of polynomials in S, which when evaluated on the j omega axis gives you some kind of resemblance to the characteristic you desire. We have seen several categories of approximation. One is of course based on the Taylor series, and that is the Butterworth approximation. We have also seen how you can do a minimax approximation where you constrain the maximum error in the approximation band to be minimum, and that is the Chebyshev family of filters. Then we saw how we could make the inverse Chebyshev family, where you try and approximate the stop band rather than the pass band. And then we said, okay, this is fine. How do you go about trying to realize a network which gives you the response that one desires? So we did a bit of network synthesis. In particular, we covered the synthesis of doubly terminated ladder networks, where we learned how to synthesize Butterworth filters, odd order Chebyshev and odd order inverse Chebyshev networks. The next step, of course, is to figure out how one can use the knowledge that we have gained so far in synthesizing other kinds of filters. For example, we have spent a lot of time this whole month looking at low pass filters. We would like to figure out how one goes and does other kinds of filters, namely high pass, band pass and band stop. One approach could be to say, hey, we know how the basic idea works. So one thing to do is say, okay, you want a brick wall band pass characteristic, and we go through the same process that we went through for the low pass case. That is, express this as whatever n of s by d of s. Find an even degree ratio of a polynomial, or rather a ratio of polynomials of even degree which approximates this magnitude. Then you go and factor it, and then you get the ratio of polynomials in S, where the magnitude approximates the band pass response rather than the low pass response. Okay. Another thing you can say is, hey, I spent all this time and effort trying to figure out low pass. Is there something I can do to kind of figure out high pass, band pass and band stop? Because if you think about it, all that we are doing is that the brick wall is moving, is either a subtracted version of the brick wall. 1 minus the brick wall gives you a high pass, right? The brick wall moved gives you band pass, and the moved brick wall minus 1 gives you band stop. So it seems as if it should be possible to exploit all the knowledge that we have gained so far, rather than start from scratch all over again. Okay. So let's try and figure this out. Before that, let me draw your attention to a very simple thing. The simplest of all these techniques, and let's say you had a filter, some characteristic with some critical frequency omega naught. Okay. So far, whatever we have seen, what is this critical frequency? In the Butterworth case, it has been the 3 dB bandwidth. In the Chebyshev case, it's been the pass band edge. Okay, and in the inverse Chebyshev case, it's been the stop band edge. In all these cases, that critical frequency was chosen to be 1 radian per second. Okay. Now from this we have figured out. Let's say this was some h of s. Now what if we wanted the same shape, right, but the critical frequency moved to omega naught? Okay, so the answer seems h of s by okay now okay. So in other words, all that happens at a frequency, whatever happens at 0 here in the original filter will happen at 0 in the transformed filter. Okay, so this is the original filter or the prototype filter. And this is the so-called transformed filter. Okay. So this simple transformation can be seen in several ways. All of us agree that you have to replace omega in the original transfer function with omega by omega naught to get the transformed filter. But why did you say omega by omega naught? Why not omega being replaced by square root of omega by omega naught? Or omega by omega naught the whole square? Okay. Any? Pardon?
Shape will change.
Shape will not change, right? I mean, so in other words, replacing omega with some function of omega, okay, will not be possible for arbitrary f of omega if one is interested in synthesizing a physically realizable network transfer function. Okay, all right. So we'll have to figure out what special f of omega, okay, will result in a physically realizable network. Does this make sense? Okay. Now, and of course, in the low pass to low pass case, for example, this transformation, it does. I mean, it luckily turns out that the network is indeed realizable. It's pretty straightforward to see. So if omega has to be replaced by omega naught, all that it means is that j omega has to be replaced with j omega by omega naught, right? Which implies s has to be replaced with s by omega naught. Okay. Now this means that an inductor whose impedance is SL has to be replaced with an impedance which goes as SL by omega naught, which also happens to be an inductor because of the special nature of this function. Okay. So in other words, an inductor L gets replaced by an inductor of value L by omega naught. Similarly, a capacitance whose admittance is SC must be replaced by an element whose admittance is what? S is to get replaced by S by omega naught this time C. So in other words, the capacitance gets replaced by C by omega naught. You understand? Okay. All right. So what have we seen? We have seen that one reactance, so reactance in the original network becomes a reactance in the transform network. What happens to the resistors? They remain the same because there is no S in the expression for either the impedance or admittance of a resistor. Oh, sorry, oops. Sorry, yes, absolutely. Correct? Okay. So now the question is, so this is what is called, it's quite trivial, right? This is what is called the low pass to low pass transformation. This is a way of getting a low pass filter with the critical frequency moved from 1 to some arbitrary frequency omega naught. Okay, and in the network, all that you need to do is to replace every inductor by another inductor of value L by omega naught, and every capacitor by another capacitor of value C by omega naught. Correct? So now, one can ask the question, we can take this to the next level and say, hey, is there an f of omega? So if I replace omega in the original network or the original transfer function by some f of omega, correct? Can you tell me what conditions f of omega must satisfy in order that the network is physically realizable? Evidently, all f of omegas will not result in a physically realizable network. Okay. So in other words, if omega has to transfer, is transformed by some f of omega, then j omega must transform to j f of omega. Correct? So reactance in the original network transforms to another reactance. So reactance in the original network or the prototype transforms to another reactance in the, let me call this the final network. Does it make sense? So in the original network, the only elements you had were resistors, okay, which do not depend on S or on omega, so they remain the same. You had inductors and capacitors, right? And the the impedance as a function of omega is purely imaginary. Either the impedance or the admittance are imaginary for all inductors and capacitors. Now if you replace omega with f of omega, all that is happening is that this transformed element, now instead of an inductor you are supposed to have an element whose reactance as a function of frequency goes as not as j omega but j f of omega. Okay, and similarly earlier if you had a capacitor, you are supposed to replace it with a physically realizable element, okay, which goes as, whose reactance goes as, whose impedance goes as 1 over j f of omega, or whose admittance goes as j times f of omega. So in other words, we have to figure out what f of omegas will result, are physically realizable. Does it make sense? Okay. Now, in the transform network, please note that these elements, every inductor has now transformed into another reactance, okay, which again is purely imaginary, right? It's J times f of omega, correct? So the impedance of this box, this capacitor is now, the inductor in the original network has transformed into another box whose impedance is purely imaginary. Similarly, a capacitance is transformed into another box whose impedance / admittance is also purely imaginary. So if you have an impedance or if your admittance which is purely imaginary, and if it is physically realizable using lumped elements, then it must be made of a combination of inductors and capacitors. Is this clear? Okay. So in other words, we are trying to therefore come up with functions of omega such that J times f of omega is the impedance or admittance of a lossless network, which consists of inductors and capacitors. Yes, sir.
So why is it necessary that f of omega should be real? We just need the transform network to be physically realizable.
Correct.
If you have a complex function,
yes.
then you can have a resistor.
Yes, you can. But there are two answers to this. There are two reasons for this. One, of course, is that it's easiest to work with a real function. Two, we saw in the network synthesis part that if the LC network is lossless and if it's equally terminated on both sides, then the sensitivity of the realized transfer function to variations in inductors and capacitors. You've all done the the Monte Carlo stuff, right? And you've seen that for yourself that it is indeed true, right? Because the reflection coefficient cannot physically, its magnitude cannot go below 0, right? So if you want the low sensitivity property, then you want the stuff inside the box, right, to be lossless, which will happen if you replace every inductor / capacitor with a combination of only lossless elements, so that the attractive property of low sensitivity is inherited even in the transform filter. In other words, it doesn't make sense to have a low sensitive prototype and then you have this transformation and the transformation screws things up and the transform network has got high sensitivity. You understand? What he's asking is, why do you assume that this function f of omega is a real function, right? Why can't you have a complex function such that still on the real axis, as long as this is satisfied, this is okay. Okay, all right. So
sensitivity, it's also lossless.
pardon?
Mentioned the sensitivity, it's also lossless in the end. So that I'm not able to.
No, that's the sensitivity comes because of the losslessness. You understand? Why is an equally terminated ladder less sensitive than an unequally terminated ladder? Right? So at the maximum of transmission, only in an equally terminated network is the reflection coefficient 0. Right? In the unequally terminated network, the reflection coefficient only goes to a minimum, it does not go to 0, which is why when you run the Monte Carlo sims, you see that the sensitivity of the unequally terminated ladder is more than the sensitivity of the equally terminated ladder. Okay. So in other words, if you take the original network and replace every inductor / capacitor with some combination of inductors and capacitors, so that the transform network also is lossless, then the transform network will inherit the low sensitivity properties of the prototype. Correct? So since one reactance transforms to another reactance, these all these families of transformations are sometimes called reactance transformations. Since inductors slash capacitors in the prototype transform to a combination of LC impedances which are basically lossless. So, in other words, what we are therefore interested in is what are the properties of, what are the impedance properties of the impedance of a network made with only L's and C's. Does it make sense? Okay. All right. So, in other words, the conditions on f of omega which make it realizable is equivalent to saying, hey, let me go and try and study the properties of lossless LC networks, because we are going to replace the L with some j times f of omega, okay, which means that it must be lossless, which means that it must be, if it is to be physically realizable, it must be realized as a combination of L and C, which means that studying the properties of f of omega is equivalent to studying the properties of the driving point impedance or the admittance of a lossless LC network. Is this clear? Okay. Now, yes, one thing. The other thing I want to point out is that whatever happens in the original network at omega equal to 0 will happen in the transformed network at so, okay, whatever happens in the original network or the prototype network at omega equal to 0 will happen now occur at f of omega equal to 0, right, or at the zeros of f of omega. Does it make sense? Please note that since f of omega is basically coming from a combination of inductors and capacitors, it must follow that it must also be a ratio of polynomials in S slash j omega, correct? So, since it's a ratio of polynomials, it must have, you know, places where it goes to 0 and places where f of omega goes to infinity. Okay, so so clearly, since whatever happens at omega equal to 0 at DC in the original network will happen now at frequencies where f of omega goes to 0, and those frequencies are the zeros of f of omega. Okay. Now, whatever happens similarly, whatever happens in the prototype at omega equal to infinity will occur at frequencies where f of omega equal to infinity or at the poles of, or at the frequencies where f of omega goes to infinity. Does this make sense? Okay. Now turning this upside down, whatever be the nature of f of omega, if you want this is the low pass, let's say you want to transform this into a band pass like this, what all should the constraints on f of omega be? Whatever is happening in the low pass at 0 must happen in the band pass at omega naught, or rather let's say I will shift it to, just to be more specific, I want this to happen at, I want a band pass filter centered at 1, let's say. So whatever happens in the prototype at DC must happen in the band pass prototype at 1, and is that only 1 or there is something else? So whatever happens, the response must be symmetric, so whatever happens at 1 must also happen at -1, okay. So 0 in the prototype must transform to 1 and -1, whatever happens at 0 must happen at 1 and -1, whatever happens at infinity in the, pardon? 1 comma -1, correct. Whatever happens at 0, this man, this part, that will come to, right? Okay. All right. So at the very least 0 must go to 1 and -1. Is that clear, Shravan Siddharth? Okay. And whatever happens at plus minus infinity, all the action that's happening at plus minus infinity in the original network must happen at 0. Very good. 0 plus minus infinity. Okay. All right. So what is the simplest ratio of polynomials you can find, which so in other words 1 and -1 are the frequencies at which zeros of f of omega, correct, and 0 and plus minus infinity are the poles of f of omega. Why 0? So whatever, say you want a band pass filter, right? So you want 0 attenuation here and at infinity. So whatever happens at infinity in the low pass prototype is happening at both 0 plus infinity and minus infinity. Is that clear? Okay. So f of omega must at least look like omega square omega minus 1 into omega plus 1 by omega. Okay, this still doesn't mean that the network will be physically realizable, okay, but it must look like this, okay. And there could be other factors which don't have real zeros and real poles, but at least omega minus 1 into omega plus 1, which is omega square minus 1 by omega, must be a factor of f of omega. Does this make sense? Okay. So now let me and similarly you can come up with at least the minimum required for other transformations. For example, let's say you want this, the low pass, to go to high pass. So this is 1, this is 1.
So bringing in other factors might affect the shape.
Yes, it might affect the shape. Yes. Okay.
Basically, you only need a constant time.
Well, okay. The comment made is why do you need the other factors at all? Why don't we just put a constant of proportionality and move on, right? At this point, we still don't know if this is realizable or not. I mean, eventually, let me give you the climax. It turns out that this is indeed realizable. Okay, and those of you who really have networks, know networks like the back of your palm. Okay. Can somebody look at this and tell me what kind of impedance will give you this? So inductor becomes inductor and capacitor, right? I mean, this is no way of deriving the what do you call the transformation. You understand? I mean, this is as much intuition as you can get with the knowledge we have, right? We want this to go to this, we want that to go to that, which means this must be a factor. The fact that this is the only thing needs a little bit of more what do you call rigor, and since it's quite elegant, I'll just go through it. Anyway, so let me also, since there's very little time today, I will also just give you the intuition behind these other transformations. So here in the high pass, if you want this to transform to this, what all happens? The action that's happening at DC plus minus infinity. Okay, the action that happens at infinity at 0, and 1 should happen at 1. Okay. Okay. So what is the 1 by omega? You understand? So f of omega must be, or rather let me do it systematically. So f of omega must have zeros at infinity and poles at 0. Okay, the simplest function I can think of which does this is 1 by omega. So omega must be replaced by something which is, so f of omega must be proportional to 1 by omega. Does it make sense? Alright, there may be other factors which we don't know what they are, but at least 1 by omega must be a part of the whole thing of f of omega. The rest of it, what do you call, can should definitely not have any more real frequencies at which it either goes to 0 or infinity. Does it make sense? Okay, so now the time has come to kind of look at the low pass to high pass we have done, low pass to band pass we have done. We have, gotten intuition. We have not done anything. We have gotten intuition. The low pass to band stop transformation. So what happens at infinity in the prototype must happen at 1. Very good. We'll make Chandri choose this to be 1. Plus minus 1. Very good. So whatever happens at infinity must happen at, okay, and whatever happens at 0 must happen at 0 plus minus infinity. So f of omega must go to 0 at 0 and plus minus So it will be omega plus 1 into omega minus 1. Does it make sense? And again, those of you who are little still remember your network stuff, you would be able to immediately recognize that this corresponds to replacing an inductor with a parallel combination of L and C. Okay, all right. So, so again, I'd like to repeat that it doesn't mean that the f of omega that we have come up with seems pretty straightforward. It just doesn't mean that this is a realizable f of omega. In other words, it doesn't mean that an inductor in the prototype or a capacitor in the prototype will transform to a realizable impedance when you plug in f of omega. Is this clear? Okay. So let me quickly digress a little bit, and since study of omega, f of omega, the properties of f of omega is nothing but the study of the properties of the driving point impedance / admittance of a lossless LC network. We might as well figure out the properties of lossless LC impedances. First thing, of course, if Z of S is the impedance of a lossless LC network, okay, this is the voltage by current. You can think of the current as the input and the voltage as the response, or vice versa. You think of the voltage as the input and current as the response. Since this is a physical system which where the nothing can blow up, it must follow that the poles of Z of S we don't know, we know where they cannot be. Cannot be in the right half plane. Okay. What about in the left half plane? If they are complex, fine, there will be complex conjugate and all that, but what about left half plane? Well, yeah, so they cannot be in the left half plane because it's lossless. It's lossless, but that doesn't come out immediately out of this. The only thing we can figure out at this point is that the poles cannot be in the right half S plane. Can they be on the j omega axis? Yes, they can be on the j omega axis. Of course, if you don't know how to prove it, you just say that an inductor, for example, goes to infinity at omega equal to infinity. So omega is S is equal to plus infinity is a pole of the impedance function of an inductor, correct? So poles can be on the j omega axis. It turns out that these poles have to be simple. What is the meaning of a simple pole? It cannot have multiplicity of so you cannot have 1 by S square or S square. Okay, you can only have you cannot have two coincident poles on the j omega axis. Okay, we will prove that a little later on. But at this point, the only thing we can say is that the poles of Z of S cannot be in the RHP. What about the zeros of Z of S? Yes. Any opinions? Pardon? Correct. So Y of S also cannot blow up because Y of S can be thought of as the response function when you apply voltage and measure the current. Okay. So the poles of Z of S or Y of S cannot be in the RHP. You can have poles on the poles / zeros can be on the j omega axis. Okay. Now draw your attention to anybody got class at 12? Oh, okay, then I'll stop here.